So here's what I have today. We're going to be talking about the KSP and different things that you can do with it. This is what we did yesterday. We saw that you can use things that are slightly soluble. Remember, the Zubdals choose not to use the word insoluble because everything will dissolve to some extent. For many things, it's a very small extent, but it will still partially dissolve. So we come up with an equilibrium for the dissolving process. Anything with a K value for the equilibrium of less than 1 is considered to be slightly soluble. So that's what we focus on in this chapter. This is what we did yesterday. If you're given the solubility of something, you can make up an ice table for it. You've got the solid breaking down into the two ions that it breaks into. The ice table would be, you have a solid over here, so we don't care about its concentration. It doesn't really even have a definition of its concentration. You don't start with any of the products, so that would be 0 and that would be 0. The change, though, even though this doesn't have a defined solubility when it's a solid, some of it does dissolve. So the amount that dissolves is considered its solubility. And that goes down by some amount x. When that goes down by x, that and that go up by x. And so we have an ice table that we filled out, and we can use the K value. In this case, we're calculating the K value. But the K value is the same all the time. It's products over reactants. Since we have a solid reactant, we don't put it into the K expression. So really, it's going to be x squared equals the K value. Now we know what x is. It's this term right here, the solubility. If that goes down by x, then that go up by x. What if one of the coefficients is a 2? Then you'd have to go up by 2x. Yeah? So that's what we were up to yesterday. We actually calculated the solubility, or the KSP, and that's where we quit. Yeah. Spencer, let's move on. Can I have you take a moment, and even though my arrows are a little bit off, try this problem. It's not that hard, but you see we have a 2 in it.
Can you tell me what
What's that? I'd say it's pretty Mickey Mouse. E-Man, what are you saying?
What am I doing?
So you can fill in an ice table for this. Remembering that solids, really, we care about concentrations of gases and aqueous things, not solids or liquids. So the solids we don't care about. Drew, do you pick it up when I'm writing on the board from that end? Mm-hmm. The ice table out generically. Didn't really need to because the problem tells us that the equilibrium concentration of the silver ion is 2.2 times 10 to the negative fourth. It's more appropriate really to put the 2.2 times 10 to the negative fourth in and just leave the x's out. But I put the x's in. What would this term be then? What's the oxalate concentration?
0.00011.
Yeah, half of this. Half of that. Because they are produced in a 2-to-1 ratio. So if you know the silver concentration, then you're going to know the oxalate concentration, which is going to be half of it. The solubility of this thing would be the 1.1 times 10 to the negative fourth. It's also half of that silver concentration. So the KSP is the silver concentration squared because of that coefficient of 2. So it's going to look like this. No, I'll just put the numbers in. 2.2 times 10 to the negative 4th squared times 1.1 times 10 to the negative 4th. Is that what you did? And you get something times 10 to the negative 12th when you're done? The thing is, just remember to square it. Watch out. There's nothing really new that you're going to learn today. It's all equilibrium and things that we've been using and learned about. We're building on it in a different context. So the context has changed, but the mechanics of doing equilibrium problems are all exactly the same as we've done before. So you get, what number do you get? 5.3. Keep everything to 2 sig figs, because the k values are going to be 2 sig figs, unless they're 1. You don't ever need 3 sig figs in this chapter. Remember, the k values don't have a unit, so even though those were a molarity, you just give it no unit. Yeah. Anybody have any questions about that? Spencer, let's go on to another one. Would you try this? Now, let me just say this too. You're going to find, as you do a few KSP problems, you're going to find that it's pretty easy. This is not a terribly difficult chapter or concept, but I really want to recommend that you stay very organized and do an ice table for every problem. Because when you do that, and you have a sense of what the changes are and what your equilibrium concentrations are, that's what makes the problems easy. If you start taking shortcuts, it's easy to make mistakes, too. Yes?
When you want us to find the solubility, does that mean we should say it's like slightly insoluble?
No, you'll have a numerical value. The x term here, this is the solubility. So when I ask for the solubility, that's what you're solving for, x. The amount of solid that dissolves.
Oh, I just realized we're wearing Hawaiian shirt. What's Hawaiian?
Oh, yeah. So this one is very similar. I would suggest that you do this. Make your ice table, circle the thing in the ice table that you're trying to find. So that when you go through the problem and you get an answer for x, you look back up here and you know what to do with it. Staying organized, I think, makes this chapter, the entire chapter, really doable. Just remember that. Take the time to do an ice table. Circle the thing in the ice table that you need. It's not bad. Did you get an answer already for this one? -2?
Bless you. Bless you.
Just kidding.
I think that's right. I think that's right.
Because it's 4x cubed, right?
Yep. You're given the KSP value, it's 1.2 times 10 to the negative fifth. And that's equal to that times that. Now that's squared times that, so it's going to be 2x quantity squared. So yeah, you do double the x value and still square it. So it's kind of like you're double dipping on anything that doesn't have a 1 coefficient, and that is what happens. And then that's times x, so don't forget that second x as well. So just solve for x in this case. This term right here is 4x squared times another x is going to make it 4x cubed. So you're going to take that number, divide by the 4, and then take the cube root of it to get your x value, which is what we're looking for, the solubility. So you get 0.014 molarity. Everybody get that?
That's really fine.
Yeah. Who's missing that makes it normally loud?
Kyle.
Yeah.
Oh, yeah,
Kyle.
Kyle.
Oh,
Oh, my God.
Whoa.
I just,
Whoa.
I feel it.
All right.
yeah.
on.
He's gonna watch
Yeah,
this
that's-
video
he's
and be
gonna watch
like,
this.
everybody hates
Kyle, we love
Don't
you.
write this down. You have a comparison. Which one is more soluble, nickel carbonate or barium chromate? And you're given the K values. Can you just compare the K values and tell which one is more soluble?
No.
Yeah.
Yes.
No.
In this case, you can.
Oh, does it depend on the coefficient?
It's a 1-to-1.
Yes.
Everything's
Yes.
1-to-1.
Yes, it does. The one with the higher K value, which one does have the higher K value?
Nickel carbonate.
This one does. This is 10 to the negative 7th power. This is 10 to the negative 11th power. So yeah, this one is more soluble. It's got the higher K. Let's go on to the next slide. We're going to come back to this one and talk about it. Now I'm going to have you compare these two with their K values. Is MNS more soluble or is iron 2 hydroxide?
We don't know.
Hard to
Higher K value in this one than in this one. However, what's different about these two?
coefficient.
There's 2 hydroxide.
This one doesn't, well, this one breaks up into 2. This one breaks up into 3 ions. Does that make a difference?
Yes.
Yeah. When you do the ice tables, this one is going to come up with an equilibrium concentration of X and X. That's going to be X squared equals the KSP. This one's going to be X and 2X. So that's going to be 4X cubed equals KSP. Are you with me on that? So in this one, to get the solubility, you have to take the square root of the K. This one, when you find the solubility, you have to take the cube root of the K.
That would be even smaller than, wouldn't it?
So what is bigger, the square root of this number or the cube root of this number? Do it on your calculator.
That's a good one.
Uh-oh.
Which one?
Yeah.
This one is square root.
Yeah. That one
This
you
one is
just
cube.
divide by 4 and then just
Yeah. Go ahead, I'll wait for you. In fact, I'll write it down when you have it.
The first one is 4.8
Oh, I'm not going fast enough.
Yeah, I think it's.
So the MNS, that's simple, you just take the
Whoa,
square root of
never
it.
mind.
Is 4.8 times 10,
Negative 7.
the negative 10. No, 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 no. Come on.
Negative 7.
Negative 7.
I thought you said 10.
I said 7.
She says.
Wow, we actually got we got
Okay, so
3 on the power of 10.
Find the X value for this one, divide by 4, and then take the cube root. That's FeOH taken twice.
You have lab and base over it's negative 7.7.
Now look at this.
what?
The iron hydroxide had the smaller K value, but it winds up, because we had to take the cube root of it, having the higher solubility. So, can you generalize, when you're asked to compare the solubilities of two solutes,
No.
how could you quickly determine which one's more soluble?
Which one has more iron?
Yeah, the more ions. Here's what I would suggest that you do, and you might want to write this down too. In fact, I'll write it up here. Comparing solubilities. You're going to the number of ions produced take that root of KSP. I hope that makes sense. This thing gave off 2 ions, so you take the square root. This gave off 3 ions, you take the cube root of it. Yeah?
You have to divide by
Yeah, you do have to divide the 4, and I think that actually makes a difference in this case.
Why?
Most of the time, they're not as close as this is. Yeah. I would venture to say that in most cases, when you're comparing two, just work on the roots and don't even worry about the constant values.